All right, building up. So now that you understand stoichiometry, now we're going to do calculations involving a limiting reactant. So what is a limiting reactant? A limiting reactant is the reactant that runs out first. Once it's gone, the reaction stops, even if there are other reactants left over. So they're the things that limit your reaction. Now, how are you going to be able to tell that this is a limiting reagent problem? The question will always give you an amount for more than one of the reactants. Okay, I should have just read this off here because it was written so much nicer. But when the question gives more than one reactant quantity and asks about a product formed, you're going to know that one of the reactants is going to limit the reaction. And our job is to figure out which one. So a fully worked out example is here. If 50 grams of aluminum are reacted with 50 grams of hydrochloric acid, how much hydrogen gas is produced? So the first thing we're going to do is write the equation. We've got aluminum, which is not diatomic, so we're just going to put aluminum, it's a solid, plus the hydrochloric acid, aqueous, is going to produce hydrogen gas. And then what else? Well, it's going to produce the aluminum chloride. Okay, so this is my reaction. I'm going to now balance it, right? So I got to check my coefficients. I've done all that work for you so that 2 aluminums and 6 hydrochloric acids produces 3 hydrogens, which is diatomic, and the 2 aluminum chlorides. Then I'm going to write what we know, just like we did with the stoichiometry problems, right? We started by saying how much of what do I have and what do I want to know how much I'm needing or producing. Whereas this time, they're going to give you two amounts. They give you that 50 grams of aluminum is reacting with 50 grams of hydrochloric acid, and they want to know how much hydrogen gas is produced. The question is, which one of these is the limiter? Okay, so the way that we do it is we now convert the mass of each reactant into moles. So we're going to take the aluminum. We had 50 grams of aluminum. Each mole of aluminum weighs 26.98 grams. So we do 50 divided by 26.98, and we get there's 1.853224611 moles of aluminum, right? That's how many moles of aluminum are in 50 grams. We might use this answer later, so if you're good with your store and recall on your calculator, I would store this as A. Otherwise, make sure you write down at least 4 decimal places to maintain accuracy, because we're going to need one of these numbers again, and you don't want to round until your final answer. So either write down at least 4 decimal places or store this as A in your calculator to be used later. Then we're going to do the same thing with the other mass. So we also have 50 grams of hydrochloric acid. Each mole of hydrochloric acid is composed of hydrogen and a chlorine. So I've just written the molar mass. Instead of finding it outside the problem, I wrote it within the problem. Then I do 50 divided by that molar mass, and I end up with 1.3714 moles of hydrochloric acid. And again, I might use this number again, so I would store it as B. So one of these moles is limiting my reaction. What you're going to do now is the part that determines which one is the limiter. Now, depending upon what course you've taken, what instructor you've had, this can be done a lot of different ways. In fact, I've never done it the way that's written here, but when I looked at this, I was like, oh, this makes so much sense to me. So what I will say is that this step can vary. Okay, I know that if you're taking a Mary Ann's Chem 50 course, I think you take both of the amounts of moles and then divide it by the coefficients in the formula, and then you look to see which one's less, and it's the limiter. I sometimes take the equations all the way to completion so that I see, well, how much of the hydrogen do each of these equations produce? And then the one that it produces less, I'm like, that was the limiter. But then I saw this when I was going through, and if you're coming from an Ellie's Chem 50, this is the way she does it, and I actually quite like it. And what she does is she takes one of the two answers, it doesn't matter which one, and says, okay, this is how many moles of, for example, hydrochloric acid I have, and does the mole to mole ratio to your other reactant. So it says, okay, this 1.3714111 moles of hydrochloric acid would need how many moles of hydrochloric acid to be fully reacted? So we convert from moles of hydrochloric acid, which there's 6. 2 moles of aluminum, which there's 2. And we get an answer of 0.47 or 4571, blah, blah, blah. That's how many moles of aluminum would be needed to completely react all the moles of hydrochloric acid. So then you look to see, well, we have 1.85, blah, 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 moles of aluminum. We need 0.457, so obviously the aluminum is in excess and your hydrochloric acid is limiting the reaction. So what you do is you completely ignore the hydrochloric acid because it was, or sorry, not the hydrochloric acid, you completely ignore the aluminum because it was in excess, and you use the hydrochloric acid because it was the limiter. Okay, so the hydrochloric acid is the limiting reagent. So then you go back and start with, I have this many moles of hydrochloric acid. I'm going to now go from moles of hydrochloric acid into moles of hydrogen. And then I'm going to multiply that by the molar mass of hydrogen. So 1 mole of hydrogen is composed of 2 hydrogen molecules. So I would type into my calculator, recall, and then this was my A, if you did that, times 3 divided by 6, and then times 2 times 1.008, or maybe you've calculated that outside of the formula. And you would end up producing 1.38 grams of hydrogen. So limiting reagent problems aren't something where there's a one size fits all. There are lots of ways of determining who the limiting reagent is and then how many grams of your product will be produced. I don't care which way you do it as long as you understand what you did. So if you're coming from Marianne's Chem 50, you might divide by the coefficient in the formula. If you're coming from Ellie's Chem 50, you would do this here. And then if you've ever talked to me, maybe you're like, hey, it's not that much more work just to go from grams of hydrochloric acid all the way to grams of hydrogen, grams of aluminum all the way to grams of hydrogen, and then just see which one produces less. So if you don't know what to do, come and talk to me, and I can help you. We'll probably cover this one in class, but just try a bunch and see if you've got them. All right, so let's try an example. And if you've got this, feel free to pause the video and just go for it. But if you're feeling a little bit confused, I'll just talk you through another one. So here we go. We've got iron 3 oxide. It's iron 3 plus and an oxygen, which is 2 minus. So that's going to make an Fe2O3. Now they've told me the state of this one. It's not so important to include the states all the time, but if it does state them, I do put them in there. And it's reacting with carbon monoxide, so 1 oxygen gas. And it's producing elemental iron, which I would guess would be a solid, but it doesn't tell me, so I'm just going to leave it off. And carbon dioxide, which again, I would guess would be a gas, but I don't know for sure, so I'm going to leave that off. Okay. Tells me to calculate the mass of iron produced when 75 grams of iron 3 oxide is reacting with 75 grams of carbon monoxide. So I know for sure this is going to be a limiting reagent problem because they've given me the mass of both of my reactants and asked me for how much of one of my products is produced. Before I can start doing all the work, I have to look at how to balance this reaction. Now, usually we start with our metals. But I will admit to you that I started with the metals the first time I did this, and then it just went in such a circle that I was like, I'm just going to refilm this video. So because there's only 1 iron on the right-hand side, it is so easy to adjust in the end that I'm just going to leave it till the end. Let's start with our oxygens. So our carbons are balanced, right? 1 on the left and 1 on the right, but our oxygens, we have 3 plus 1 on the left, so we have 4, and then we have 2 on the right. And what happened when I first filmed this video is I went and said, okay, let's make this odd number on the left even. And then it took me down this whole rabbit hole that I was like, you know what, I'm just going to film this again and make it easier. So just so you know, these are not always easy, but I didn't want to make you an hour-long video of me trying to balance this equation. So here's a more polished version. What I would look at instead is the fact that I could put a 3 on this oxygen because then I'm going to make this odd number even by doing an odd plus an odd, right? And that's very specific to this example. It doesn't always work this way, but it worked really well for this one. So I had 3 oxygens in my first compound and 3 oxygens in my second, which makes 6. So then I could put a 3 on my carbon dioxide, and now my carbons are balanced. And then all I have to do is put a 2 on my iron. And just like that, it's balanced. But trust me, it took me a long time the first time I was trying it. So now we're going to start the limiting reagent part. So you're going to take both of your substances, so both of your reactants, and take them to moles. Okay, so I'm going to start with my 75 grams of iron 3 oxide, and I'm going to convert it to moles. I know that 1 mole of iron 3, iron 3 oxide, it's hard to say that and write it too, but iron 3 oxide weighs how much? Well, it's going to be 2 irons, where each iron is 55.85, plus 3 of the oxygens, which are each 16. And again, if you want to do molar masses outside, that's fine. I just tend to get to a point with these where I'm like, it's too much writing. So I'm doing it within my formula, and that's just personal preference. You can do it however you want. So I'm going to take that 75 and I'm going to divide it by bracket 2 times 55.85 plus 3 times 16 unbracket equals. And I will say the downside of doing that is that if you need that molar mass again, you haven't written it calculated out. So, choose your poison. Okay, but this ends up as 0.4696. Keep at least 4 decimal places, ... Even better, I'm going to store this as A. So I'm going to hit my calculator, blue, store on my calculator because I have a sharp, it says alpha. So it says which alpha character do you want to save it as? I'm going to save it as A. And now I can clear my calculator. I can do anything I want, and that thing is saved as A. Then I'm going to do the same thing with my carbon monoxide. So I've got 75 grams of my carbon monoxide. And again, I'm going to figure out how much does 1 mole of carbon monoxide weigh. Well, it's 1 carbon, which is what, 12.01, and it's 1 oxygen, which is 16. So then I'm going to plug into my calculator, 75 divided by bracket 12.01 plus 16 unbracket equals, and then I get 2.6776 ... And I'm going to store this as B for just in case. Okay, now I have to figure out who's the limiter. So again, your choice. You can take the iron 3 oxide and divide by 1, and take the carbon monoxide and divide by 3, and then compare those two answers. Or what works in my head really nicely is to do one of the two things. I can either compare, like, if I have X moles of something, how many moles of the other thing will I need? Or I can just make them both go to product. So I'm going to do it the way that it was in the example. I'm going to take the moles of iron because I'm pretty sure it's going to be the limiter. So I'm going to take that 0.4696 moles of iron 3 oxide, and I'm going to do the mole to mole ratio into carbon monoxide. So we know that 1 mole of iron 2 oxide needs 3 moles of carbon monoxide. So I'm going to take that recall A, and I'm going to times it by 3. I would need 1.4088 ... moles of carbon monoxide. Since now this is my actual, this is my need. Since my moles of aluminum chloride or aluminum actual is more than my moles of my aluminum that I need, therefore it's in excess. So my limiter is going to be what I thought it was, which is my iron 3 oxide. So then you're going to start at this point here. You're going to say, okay, I'm going to take it from that 0.4696 ... maybe recall A, moles of iron oxide. And I'm going to see how many grams of the, I've forgotten what we're trying to see, iron. Yep. How many grams of the iron is going to be produced. So from my formula, I know that 1 mole of iron 3 oxide produces, I'm just going to shrink this down. I just need to see my top. Produces 2 moles of iron. And then I know that 1 mole of iron weighs 55.85 grams. So typing into my calculator, I'm going to hit recall A, or I'm going to type down at least those 4 decimal places. I'm going to times it by 2. I'm going to times it by 55.85. And I end up with, to 3 sig figs, 52.5 grams of iron would be produced with aluminum in excess. Awesome. And if you're in math or Chem 50, they would be like, and how much excess aluminum did you have? Yeah, and we won't be using this skill for a while. I think this comes back way at the end of like unit 6 of Chem 60, but this is something that is an expectation that you can do.